number 45 is a problem that looks a lot like the way electrical power is generated. So if you look at the system here, there's sort of this semicircle of wire right here, which is immersed in a magnetic field. And what can happen then, according to the system here, is like this crank can be turned over here. And if this crank is turned, someone starts turning the crank, this semicircular loop will start rotating in the magnetic field. And what the question wants then is, what is the induced current in this loop? And some other things about, will this light bulb come on, and so on and so forth. So let's see if we can take a look at this one here. The critical part about this problem here is you want to analyze what the flux is through this semicircular loop right here, the changing magnetic flux. And the reason why the flux is going to change this time, the most general expression we have for magnetic flux is that it's magnetic field times area times the cosine of the angle between the magnetic field and the normal to the area in this case here. And it's not the B that's changing in this case. The B is always constant. The A isn't changing either. It's always a semicircle here. In fact, the area here is always going to be something like 1/2 times pi r squared. Of course, the 1/2 because it's a semicircle. It's the angle that's changing now. So this is sort of a unique problem in that aspect. And that the angle now is going to be something like 2 pi times f times t. Now, where did I get that from? Well, I know it's a trig function. And if you want to make a trig function behave nicely in the time domain, you also have to put a 2 pi in to scale it. That way the cosine will make all its proper transitions every 0 and pi over 2 and 2 pi. F is the frequency at which the handle is being turned, and of course t is time. So if I put all that together there, I'll get the magnetic flux then is B times A times the cosine of 2 pi f times t, something like that. So this is what my magnetic flux is. And again, I'll repeat again. The B isn't changing. The A isn't changing. It's that angle which is changing because that crank is being turned. The angle changes at the rate 2 pi f times t. In other contexts, maybe physics 132 or something like that, this term here may very well have been cosine of omega times t. Looks a lot simpler. But of course, that's exactly the relation. Omega's O is like 2 pi f, something like that. It's radio frequency versus just, natural frequency in hertz, if you will. So the point is that you have a magnetic flux now that has a very explicit time dependence. So if you come in now, you know that Faraday's law says the induced EMF is minus n times the time rate of change of that flux, something like that. Then the induced EMF is minus n. Now the time rate of change of flux, take the derivative of this thing here. I'll get B times A. Derivative of cosine is minus sine 2 pi f t, something like that. Now don't forget about the chain rule. Differentiate inside that trig function there. 2 pi f, something like that. So this is the induced EMF. Again, the B and the A are still sticking around in there, but here's that derivative of that trig function that had the time dependence in there. So I look at this thing, and this is what the induced EMF would be. It looks like it's only a one-turn coil, so we'll go ahead and drop the n out, and these minus signs sort of cancel each other. So I'm left with a BA times a 2 pi f from the chain rule times the sine of 2 pi f times t. This is the induced EMF in that coil. Does it have time dependence? Sure does. It's even 0 at some points, depending on what time it is here, because the sine function, again, if you plot the sine function as a function of time, just sort of looks like this. So there are points on here where the EMF is maximal right there, where it's 0, and where it's even minimal or maximal in the opposite sense, however you want to think about it. I think in this particular problem, or in common in these problems here, they want to know what the maximum EMF would be. And of course, the maximum EMF is at one of these points, like here or here. So it's just sort of where the whole trig function here is equal to 1, because the sine cycles through 1 and minus 1 as it goes. So you can sort of write here that the maximum EMF is something like 2 pi times B times A times F, something like that. So that would be sort of the maximum EMF for the problem. So all kinds of stuff you could sort of figure out or calculate from this. Now, typically in a problem like this here, it wants maybe to know something like about the current that would travel. Maybe this is a light bulb or something that the generator is running in there. So you drop all the way down here and go, okay, if you want the current, Ohm's law still holds. I is, of course, just say for maximal current, the maximum EMF divided by the resistance of the thing. So it would be something like 2 pi BA times the frequency over the resistance, something like that. This would be the maximum current that you'd expect to flow through the light bulb. So depending on what you do with the problem now, you can sort of put some of these things together and get things to work. Like I think in this particular problem here, it quoted that light bulb as having an R of 1 ohm and a power of 4 watts. Well, what that tells me in this case here, I know that P is equal to I squared R. That's the power equation right there. So the current that I want to get through this system here is going to be, or I squared rather, is going to be your 4 watts over your 1 ohm right there. So the maximum current that you'd want to achieve the power of 4 watts in the light bulb there is just 2 amps. So this is the current that you want. So you can start working on it yourself now, but if this is the maximum current you want, you can certainly equate that to that maximum current right there and link it to B and A and F and that sort of thing to get the problem to work out. Now I think in this particular problem here, given the parameters, I believe that the frequency you'd have to turn it out to light that light bulb was something around 405 hertz, which is just impossible, but it gives you a bit of a figure about, again, the energy question that we discussed. Like, what's going to continue to turn something in a magnetic field? If you just want to light up a little light bulb like that, you have to turn this crank at 400 times per second in order to get that to work. Not feasible, but nevertheless, that's the issue. Where's the energy going to come from?